Okay, maybe it's time to get started. So we're very happy to have Ben Freivogel from Amsterdam, who is giving us what seems to be like an experimental talk about how to build traversable wormholes. Take it away.
Okay. Yeah, thanks for inviting me. It's been a lot of fun chatting with everybody. Yeah, let me know if it's not understandable with the whole setup. Yeah, so I'm going to talk to you about how to build traversable wormholes. This is based on a paper students in Amsterdam, and also some kind of further computations we did since then. Since I don't know some people here, let me mention very briefly like the other things that I'm working on in case you're working on those things as well. So one thing that I'm working on is, that I'm not going to talk about today, is energy conditions in quantum field theory, with the view towards understanding what kind of singularity theorems are true in the semi-classical gravity. And so we proved in certain contexts certain smeared null energy conditions, which take this kind of form. So you take you smear the null components of the stress tensor for some region like this, and you get some kind of results like that. So that's one kind of ongoing thing, and if you have thoughts in that area, I'd be happy to chat. And a second thing that I've been working on, well, I guess like many people, I was trying to understand this averaging story. This one? Yeah. Okay. And the particular thing that we focused on is the statement that gravity computes certain moments of an average over states. And this was following up on some work by Jamie. So that's another thing. Those are sort of like the more ongoing things, but Raphael has heard about both of those things, so it's important to keep him entertained, so I wanted to talk about this other thing. So this is more like a little thing that we did. That was actually started as a master's project of the Susanna. But I think actually there's, it's a fun we can use to ask some quantum gravity questions. I think there's many further things that could be done with this. So I think this should be entertaining at least. So there's different motivations you could link to this. One motivation is basically how we're going to test quantum gravity. So, of course, a very exciting thing to do is a signature, if we would see some observational signature of quantum gravity in, LIGO or some kind of observations of black holes. I'm curious about your opinion. So who thinks that this will happen? Let's say within our lifetimes, to be concrete. Do you think that there's a signature of quantum gravity that we could... Okay, so people don't have the ambition to make our field an experimental science. So this would have... Sorry? Was the question about LIGO or about the entertaining? No, any kind of observations of the real universe. Yeah. Okay, let's ask again. In observations of the real, let's just say like this. Something that goes beyond GR. Okay, all right. Never mind. I withdraw the question. Okay. All right. So that would be very exciting. I think that's an interesting thing to think about. But something that seems more doable at the moment. I mean, obviously the issue here is that if you look at, merging black holes and so on, you need some pretty exotic quantum gravity effects in order to be able to see those in conceivable experiments. So a plan B for observing quantum gravity is basically using ADS-CFT. And this is something that was discussed, I guess, in papers by Lenny Susskind and Adam Brown, and then many more authors in the Bay Area for the most part. So the idea there is just that we can tease in the lab or on a quantum computer. We can simulate them. If we can simulate holographic CFTs, then we can make gravity duals, and then we can ask the gravitational questions there. Okay? So clearly that's not quite as exciting as this thing, but that might be what we can do. Okay? And it's in this second plan B that this project is relevant. Okay, so one interesting type of thing that you might try to make in this is traversable wormholes. And I think this whole discussion about probing quantum gravity in this way, to some extent, was energized by the paper by Gao-Jeffers and Wall, where they showed that we could introduce perturbations to make wormholes traversable, and then we could consider, sending observers through those wormholes to report back to us. Okay, so what we have is sort of like a different version of a traversable wormhole that gives you some new kind of dials, and it might be kind of easier to work with than this original construction. And I think there's some interesting questions there. So let me state the basic claim. So we consider, we take a holographic CFT, with a U1 global symmetry. And then we construct a rather simple Hamiltonian, which includes, the usual. So we take the usual Hamiltonian of these. So we take two copies of these things that we're going to label left and right. We have two CFTs. We have an interaction. So this is very similar to the construction of Daniel and collaborators. In this case, we have a field that's dual to a charged massless fermion. Okay, so we need a holographic CFT that, from the bulk point of view, is a charged massless fermion. This coupling, though, is on the boundary. And then we have a term that kind of looks like a chemical potential. So we take the charge associated to this symmetry, and we introduce a term like this in the Hamiltonian. Okay, so that's yes.
So U1 is common for both.
Sorry?
U1 is common for both theories. Single U1.
Yeah. So these are two of the same theory. They both have a U1.
Direct coupling violates U1 cross U1 to down to U1. What charge?
Yes, that's true. So before you couple them, you have two U1 global symmetries, one on each side. This coupling breaks that down to a single conserved charge. Okay, so we consider this thing, and the claim is that the ground state in some range of parameters. So you have two main parameters here. You have this coupling between the two theories, and you have this chemical potential type term. And the claim is that the ground state in some range of parameters is an eternal traversable wormhole. So the claim. So what I want to do is I want to construction So describe this bulk solution. I'm going to be kind of brief here because, you know, this solution is not like that novel. So this kind of coupling is very similar to what Daniel did. And also this, the way the solution looks is very similar to this wormhole of Maldacena, Melekin, and Popov, just kind of put into ADS space. But putting ADS space gives you some kind of different dials that you can turn and questions that you can ask. So that's kind of fun. But anyway, for that reason, I'm going to be a little bit brief in describing this bulk solution. When the wormhole dominates. So I'm going to talk about the phases. So what's the ground state of this Hamiltonian for different ranges of parameters. And then hopefully, if I budgeted time correctly, we'll have time, because I think the most interesting is a little bit what could be done with this kind of setup, how it connects to other things, and so on.
What dimension are you in?
Sorry?
What dimension are you in? Any dimension?
Oh, yeah. So this is going to be a very explicit thing. So the bulk is going to be 4D. Okay, so it's very conventional. Other questions? Sorry. Okay, and maybe I could mention briefly that, you know, another reason that you might be interested in building these types of things is that we just don't really understand yet what's the zoo of solutions that are allowed once you include quantum effects in the bulk, right? Like traversable wormholes were not allowed until we started including quantum effects. And so that's one approach. Another thing is maybe you like these traversable wormholes that Maldacena, Melekin, and Popov constructed. I think it's kind of hard to produce those in the real world, as far as I understand. And so this could be also just a way of producing one of those wormholes. Okay, so let me tell you about the bulk theory. Hopefully this will be a little bit boring. So the bulk action, it has, you know, the Einstein term. It has a U1 gauge field with some coupling, electric coupling G. Oh yeah, I guess we better put a cosmological constant here. And it has some fermions, which are charged under this U1 gauge group. Okay, so we have gravity, we have the gauge field, we have the massless fermions, and that's it. And now, what is the solution going to look like? Oh, yeah, so maybe I should say, so then the novel thing that we're going to have is we're going to have an interaction term, which is going to couple the two boundaries, right? So, and what this interaction term looks like as this H, which is the coupling strings, and then it's not local in the sense that it couples the two boundaries, but other than that, it's local. So it has, you know, an integral over the boundary coordinates. We call them y, and then we have the two fields at the same space-time point. Okay, so we have an interaction term. All right, so now what is this solution supposed to look like?
You don't want to borrow one of those?
Oh, yeah. Let me be a little bit. There's some bars, and actually, like, you know, it's this, and then you have to, you know, also have the thing where you exchange left and right. And okay, there's many details that are in our paper, but yeah, it's actually you can consider some. If you think in detail about these couplings, there's actually some different things you could try. So we tried a simple thing that works, but we actually didn't explore the full parameter space. But yes, the actual thing that we did is this. Okay.
You have the same coordinate system of both boundaries.
Yeah, I mean, you know, at some point you have to choose your coordinates, but in those coordinates you put this coupling. Then once you've coupled these things, then things will look weird if you change coordinates on one side.
Time goes the same way.
Yeah, so we're taking the point of view that if you just have these two, let's think of the actual like systems in the lab. So everything is kind of defined in the conventional way. So in particular, time goes in the same direction on both sides. And yeah, that's yeah. So now, what does this solution look like? Okay, so let's see if I can do a reasonable job. So I'm just going to draw a space. Okay, so the space is going to look like this. Okay, I'm sure this is very illuminating. In here we have like nearly ADS2 cross S2 in the center. Here we have out here we have Reiser-Nordstrom ADS4. So a near extremal magnetically charged black hole. There's some kind of overlap region where both of these metrics are kind of valid. Okay, we have the left boundary here, we have the right boundary here. There are some magnetic field lines that are, you know, threading this thing. So these are magnetically charged black holes. And if you feel like drawing this coupling, then you know you need to say that like you impose some coupling between this point and this point over here. Okay? Because you had these two systems in the bulk, they're far apart, but in your lab they might be right next to each other. And so you've connected some wires between this point and that point. Sorry? Yeah, so H, I guess, okay, let me draw this pink line. So there's some coupling that couples these 2 points whose strength is H. Well, the solution is going to depend on this H. So I can write a little bit what the solution looks like. Yeah, so this won't be a consistent solution when H goes to 0. So, like here, maybe an important thing to note is that in this region, well, it's there everywhere, but in this region, we have basically like a Casimir type energy due from these virtual charged fermions. Okay, so there are no real fermions in this solution, but we have these magnetic field lines. We have virtual fermions that are kind of attached to these magnetic field lines. I can be a little more explicit about this, but it's the same as in this Maldacena construction. And there's a Casimir energy, which provides the violation of the null energy condition, which you need to make this. And this Casimir energy is proportional to H. Okay, so if you would try to make this geometry without a coupling, you would have a problem, because from the bulk point of view, I'm just drawing space here, and this thing is static, okay? So this is a traversable wormhole. So from the bulk point of view, you can go from one side to the other. It has to be dual to a CFT where there's a coupling, because information has to be able to go from one CFT to the other. Okay, so that's all self-consistent. Did you?
But I guess at H equals 0, we just have Reissner-Nordstrom. Is that correct? I mean, the magnetically charged black hole exists at H equals 0.
So I'll go through the zoo of solutions, but the most obvious solution you might consider that's close to this one indeed is when H goes to 0 is just the Reissner-Nordstrom black hole, extremal, non-traversable Reissner-Nordstrom. So you could kind of think like this coupling is creating this traversable throat here. Let me say a little bit more about what this solution looks like, and like why you can compute this thing. So the metric. There's a reason I want to write this rather explicit form of the metric. Okay, so with the symmetry ansatz, the metric can be brought into this form, where we have some kind of scale factor that depends only on x. And then we have a radial coordinate. Okay, so the solution looks like this. And then we can solve numerically everywhere, or we can solve approximately analytically in these different regions for what these two functions are. Okay, the gauge field is, the usual kind of thing that creates a magnetic charge. Okay. Yeah, and then the remaining thing that you need to solve for is the amount of Casimir energy. Right. So So how do we solve for this metric? It's a fun conceptual point. It's not really new, but so what are the equations that we're going to solve? So we're going to solve the Einstein equation with the expectation value of T mu nu in here. Now, some aspects of T mu nu you can compute in a simple way, right? You have the cosmological constant, you have the gauge field, you know how to just compute those. But so this T mu nu, so there's lambda, there's f squared, in ways that you know how to compute. And then there's T mu nu, the Casimir energy. And the reason that this type of thing is usually very difficult to do is that this Casimir energy depends on the metric, right? You need to, in order to figure out the quantum state of the fields, to compute the stress tensor, you need to know the metric. And in order to know the metric, you need to know the stress tensor. So usually these equations are very difficult to solve. Of course, the most common thing that you do is you start with the classical solution, and then you perturb it a little bit. In this case, there's no classical solution like this. Classically, you can't have a traversable wormhole because of the null energy condition. Okay? So we're finding a solution to the semi-classical Einstein equations that is not close to a classical solution. So why is this tractable? And it's tractable is that this is a simple function. Okay. So what we do is we do a KK reduction on this two-sphere. And then what's left? We keep the lowest modes on the sphere. And a single 4D fermion leads to Q massless 2D fermions. Right, so this is kind of the key technical point that made this Muldesander-Melekin Popov construction work. From the 2D point of view, you need to have a lot of fields. But if you start adding a bunch of 4D fields, then you're going to renormalize the Newton constant and so on, and things will get out of control. Okay, so the key thing that works here is that a single 4D fermion leads to Q 2D fermions, and roughly these guys are in the lowest Landau levels due to this magnetic field, and they're roughly just confined to these magnetic field lines. Okay, so it's kind of like each magnetic line has a fermion attached to it. So from the 2D point of view, you have a large number of fields and so on. And then you can have a significant enough contribution to this stress tensor. Okay, so that's the first ingredient. The second ingredient, of course, is that from the 2D point of view, that this is just conformal. And so you can compute this stress tensor. And what you find is that this stress tensor, due to this Casimir energy, is equal to, so it provides, negative energy. That's what you need from it. It depends on this radial coordinate, x. And then if you care, it has kind of a tensor structure that looks like this. So it has no pressure in the sphere directions. It has a negative energy density. I thought I would remember this formula, but indeed. So there's also an H here. Yes, that's the key point. Yeah. Maybe I should just say briefly what this H does. So this H just modifies your boundary conditions, right? So if you think about ADS with a left boundary and a right boundary, what it's basically saying is that when this fermion approaches the boundary, then it mostly bounces some little part of it, comes over to the left side, and propagates through there. Okay, so it's a little bit like Pac-Man, okay, with the amplitude H. Concretely, the boundary condition is something like, there's some plus minus involved, but, psi right plus H, psi left minus is equal to 0. Some kind of boundary condition that mixes these two things. Okay, but pictorially it's just something like this. Changing this boundary condition, shifts the quantum state, it shifts the stress tensor, and that's what allows you to have this negative energy. So that's the thing that's doing the work for you. Okay, so that's the basic solution. I don't think I need to tell you more ingredients here, but maybe a nice thing to tell you about the asymptotic, one more piece of data here is what does this asymptotic solution look like? So this is a near extremal, Reisner-Nordstrom ADS, magnetically charged, and the obvious thing to compute is the shift from extremality, okay? So, and the shift from extremality, which is like the binding energy of this thing. So the mass is smaller than the extremal mass with the same charge. And maybe I want to write two different formulas for it, depending on whether the size of the horizon is bigger or smaller than the ADS scale. So this thing is equal to this thing when the horizon size is much less than L. Okay, so this R bar is the horizon size. This G, remember, is the gauge coupling. And then has a slightly different formula when R bar is bigger than L. I'm not going to write these formulas very much as we go on, because there's not, of course everything always changes for small ADS black holes versus big ADS black holes, but it kind of happens in the expected way. So the key point here is this minus sign. Okay, so seen from infinity, this thing looks like a super extremal black hole. Okay, it's a solution that's not allowed in GR. That makes sense, right? Because you want this solution to have lower energy compared to the non-traversable black hole. Okay, I think that's pretty much what I wanted to say about the bulk solution. Are there questions?
Are there also time-like, close time-like curves?
No.
That sometimes happens when you go to
I mean, this is just a static geometry, so there's not actually any kind of exotic. What's exotic is that you can make it from one boundary to the other. But, I mean, it's like this spatial geometry times time, obviously with some warp factor. But, like, this thing never goes to zero. So there's kind of nothing exciting that happens with the causal structure beyond traversability.
Right, but this coordinate system is covering the static patch, so presumably there's a behind the horizon region also.
This covers everything. So this never goes to zero. These are like non-singular coordinates that cover the whole, because this is a drawing of the spatial slice, and then you don't have the information about what happens to the time component, but that doesn't go to zero anywhere. So these coordinates cover everything.
I see. So the Penrose diagram is like just an infinite strip or something like that?
Yeah, the Penrose diagram is an infinite strip. Maybe a thing that I should have mentioned here is that this little piece of ADS2 here, if you want to glue that on, then this is a piece of like global ADS2 there, okay? And it glues to the Reiser-Nordstrom metric, but there's no singularities anywhere, there's no horizons.
Ben, is this solution stable, given that Moloseno's is metastable?
Sorry?
Is it stable, the solution?
Is it stable? Yes, but let me come to the energy scales in a moment. For the moment, this is just a solution, but I will argue that it's stable. But we have not checked everything.
Yeah, I was going to ask how large you can take mu, but I guess that's what you're going to discuss now anyway, right?
Yes. Yeah. Okay, so that's the bulk solution. And now I want to claim that it's the ground state of this Hamiltonian. So the so what we did is kind of the obvious thing. So we for wormhole geometry. Okay? So you can kind of see, I mean, obviously I'm not going to go through the whole thing, but just to be very explicit. So here we get the masses, which are, you know, the extremal mass plus delta M. Right, here we get some kind of boundary limits of these correlation functions. And then here we just get the charges. If you kind of look at this, you know, these field lines kind of have an orientation, so it's natural to think of the charges of the two black holes as being equal and opposite. Right? There's no explicit charges in this construction. Okay, but from the most natural point of view, Q right is minus Q left. Okay, and I'm sorry, but so this Q is an integer, and big Q is related to little q with the gauge coupling. So there's these factors of little g floating around, but they're not super interesting. Okay, then you have to compute this thing. You do some stuff, and in the end, what you find is that the expectation value of this thing is kind of a part that you would have from just the from black hole. So that's the extremal mass minus mu times the charge. And then you get a shift. Sorry, so I guess we're in the conventions here where this delta M is negative. Okay, so we get a negative contribution. Okay, so now the obvious question. Yeah, and okay, there's various different formulas for delta M, but this is maybe a good enough formula. Okay, now what we want to know is what dominates. So the states that we consider are, you could consider more states actually. So we consider the traversable wormhole, just the non-traversable Reisner-Nordstrom black hole, and the ADS vacuum. Let me write one kind of slightly more detailed formula. So the most convenient, what's not very obvious is whether this quantity is positive or negative. Okay, so, and that's what's going to determine kind of the phases of this thing. So it's nice to write everything in terms of r bar, the radius of the extremal black hole. Okay, so in terms of the radius of the extremal black hole, I mean, these formulas are not super important, but so you have again some kind of boring dependence on the ADS radius and the mass of the extremal black hole is given by this kind of thing. Okay, the point of writing this is that now we can see whether this whole quantity is going to be positive or negative. Okay, so I think the longest formula that I want to write here is that in the wormhole is this factor of 2. And now we have the classical contributions. So we have the mass, the charge, okay, so that's kind of the classical thing. And we have a small correction, which is due to this coupling. And then some function of r bar over L. That's not exciting. Okay, so because of the 1 over g's, these terms tend to dominate over this term, okay, up to some small correction. What you can see is, if you look at small r, there's a competition between this term and this term, right? So for small mu, then this is just a positive function. Right? This mu term is negligible compared to this. This is the same as the action for the Reisner-Nordstrom black hole, the energy for the Reisner-Nordstrom black hole. The only difference is the piece here. So in that regime, then, as you might expect, vacuum ADS dominates. On the other hand, if we go to large mu, so mu bigger than some critical mu, then this thing dominates. Okay, so if you compute more fully what the phase diagram looks like, so you can draw mu here and h here. So it's only for positive h that this Casimir energy has the right sign to support your wormhole. Okay, so for negative h, we can't have these wormholes, but so it looks something like this. So here we have vacuum ADS. Here we have the wormhole. Here we still have vacuum ADS. And here we have just the Reissner-Nordstrom extremal black hole. Okay, so that's the picture. And then it's maybe nice that there's actually a rather simple formula for what the radius looks like, at least near this point. So the radius of the black hole looks like this. Okay, so near this critical radius, then the size of the black hole goes to 0.
Even h is negative, if delta m is negative, the h square.
Yeah, this looks like it's even in h, but the thing is, if h has the wrong sign, then the solution doesn't exist. It's kind of weird that it ends up being h squared, since that's the case, but no, when h is negative, then you can only trust these formulas when h is positive.
The sign of h is meaningful relative to 0. Is that the point?
Yes.
Yeah, because like if they flip both signs, it just
Yes.
changes it.
Yeah. If you want to be more adventurous, you can also send h to 1 over h, and that will also not change anything. But not at the level of this formula. But so I kind of wrote these for small h, but you can actually compute it for arbitrary h, and then never mind.
If you elaborate, how does very small h play with large h?
Well, because like from the bulk point of view, you have these fermions, and so the effect of this h. So, okay, assuming that you can still work in the same approximation where you have quantum fields in this background and so on. From the bulk point of view, you have some fermions with some boundary condition h. H shifts those frequencies and leads to a Casimir energy. But of course, as you make h bigger, okay, you just start, the energy levels eventually just cross each other, and the Casimir energy kind of is a periodic function of h. Or maybe you could kind of say, like, because they're fermions, then they can't get large occupation numbers. Or, I know the computation, but I don't fully understand the intuition.
You said h to 1 minus h, not 1 whole.
H goes to, okay, I have to look, but our claim was, okay, I have to get back to you on that. I think that is h to 1 over h. There's a formula for this energy, which, okay, sorry, I need to review I'm sure that we wrote h to 1 over h, but I don't know all right, I think there's a whole set of different h's that give the same, that give the same energy. All right, that's a bit of a distraction. The physical thing you probably want to do is small h. Yes? Sorry?
So what happens if we just stay at mu equals 0?
Yeah, so there it looks like you're going to get some wormhole at large h, but I don't think that that's a reliable result.
Yeah, that's why I was curious, like, what tells you when it's reliable? I mean, your solution is exact, right? It's not some perturbative expansion in h or something.
Well, this is perturbative in h. We computed things in our paper that are not perturbative in h. But it is still the case that this Casimir energy is small and, it's perturbative in the sense that it's semi-classical gravity.
Okay, but so where is this expansion under control in this diagram?
Yeah, sorry, that's something that we should have said, or I should have said when I drew this diagram, but somewhere below here. Yeah, sorry, that was a significant oversight. Okay. Yeah, so here we've kind of written every. Yeah, so you want to know how. Well, so here, for example, we solve for R bar in terms of mu. So, I mean, the way it works basically is you have some formula like this, right, that has a mu in it. And now you start trying out different sizes of black hole to try to minimize this thing. Okay, so it's basically like, given your values of mu, or this may be a more useful formula, okay? Given your values of mu and h, then you start trying to minimize this function, and so then the size of the black hole is determined by mu.
Why isn't the expectation value of h just m plus delta m, or twice that, or something like that? How did that? Isn't the ADM energy also the boundary Hamiltonian expectation value?
The point is that the expectation value of this guy is m plus delta m. Now we added some terms to our Hamiltonian,
Oh, I see.
and that changed the formula for the energy. I think you could see it as, like, one way of doing it is to say you had your bulk action, which was Einstein plus certain boundary couplings here, and then you can redo the ADM thing. Yeah. Okay, so I just want to mention that there's kind of two energy scales in this problem. So one is this energy scale delta M. So that's like, let me maybe draw a picture here. So here we have the wormhole. Sorry. Here we have just the Reiser-Nordström black hole. Here we have the wormhole. This delta M here is given by this formula, right? So minus g squared h squared over r bar for small black holes. But there's also, you can also ask the question, what about like small fluctuations around the wormhole? What if you feel like exciting that thing a little bit? So there's a second energy scale here, which is fluctuations around the wormhole. And that formula in this regime is given by this same scale, 1 over r bar, and then times these couplings again, but then divided by the square root of the entropy, or whatever. You could write it in terms of L Planck, but it's a convenient way of writing it. Okay, so in this setting, then there's kind of a lot of small excitations around this black hole. I mean, these are roughly just like these excitations that are kind of living in this ADS2 throat. Of course, it's a bit subtle, right, to think about the excitations of ADS2. But if you read the recent papers over the last few years about ADS2, then the excitations are basically given by the ADS2 radius, and then there's a redshift factor, which is what tends to make these small. I don't really expect this square root of S in particular, so maybe someone has some intuition. I think I can argue for it from the point of view of like redshifts. You kind of compute the redshift of this matching surface. Maybe there should be an independent argument for why this is the gap. Okay, so what does that actually mean? So it means that if you wanted to build this thing, one way of building it is trying to let the system cool down. Then it's going to be hard to really hit this exact ground state because you have these other nearby states that are separated by a small energy gap. But on the other hand, if all you want to do is to make a wormhole, then any of these states are fine. These are all wormholes with small excitations. And then the fact that this energy gap is not particularly small, it's like much larger than the temperature that you would be interested in, then that makes it kind of a feasible thing to do. So, okay. So that's kind of the construction. Let me mention some of the open questions or like future things that we could do with this. One thing I wanted to mention, how can we use this to probe quantum gravity? So maybe you have a different idea. I haven't thought about this in a lot of detail. One thing that seems fun is to try to go across this phase transition where the ground state changes from being a wormhole, a traversable wormhole, to being vacuum ADS. Then your system has to do something that's non-perturbative, right? It needs to pinch off. So that's something that you can try to compute theoretically, and you could so you can try to compute the rate for forming or destroying the traversable wormhole. I don't know that we have any kind of estimate for the rate for that process. Okay, so you have these control parameters, this mu and h, which are just some boring dials in your theory, but then the bulk solution has to change in kind of a dramatic way. There's probably other questions you could also ask that, you know, going back to the motivation I mentioned at the beginning, you can try to, you know, send things through this wormhole and see what you can learn from that. It's not totally obvious you're going to learn about quantum gravity, right? If you don't believe this solution, then it's very interesting to try to send probes through there and see what works out. If you do believe this solution, like, okay, fine, it's just semi-classical gravity, it's not high curvature or anything. Then you might be interested in trying to go near this point where the black hole gets small and things get more quantum. Okay? But a second question is kind of other phases. Right? Because I only considered, you know, this wormhole and this vacuum solution. But say you have a theory with some explicit charges, some charged particles, which I guess typically we would have. Then you might tend to dominate when you get near this point, right? Usually small black holes, they might like. And then the reason we didn't do this is that then this analysis depends on the mass of those charges and so on. Okay, so that's why I mentioned this as a fun thing to do. That's a generic prediction that you'll go from one phase to the other. But near here, I think there would be some details about your theory, which could also be fun. But they might kind of block you from trying to get to this very small black hole. Related to this question of stability, then I think it's very interesting to ask about supersymmetric embedding of this thing, right? So at this level, we just had some U1. It's just an extremal, a near extremal magnetically charged black hole. But you would have much more control if you would make this nearly BPS, right? Once you start thinking about what all the operators in your theory, how you're going to really construct this, could there be instabilities? Then this would be a very useful thing. And people who have, I guess various people have done this, but one of them is Alejandro Castro, and they computed, you know, what's the spectrum of operators in some ADS2, and they found that the thing is only stable when it comes from some supersymmetric black hole in higher dimensions. Okay, the main thing I wanted to mention, though, is kind of how this relates to other kind of wormhole constructions. So, of course, the famous, one famous eternal traversable wormhole is this one. So in that they were an ADS2, and they're a coupling that looks very similar, right? But in a way, it's kind of quite different because it's a microscopic coupling between left and right, right? This is not like a low energy operator on the left that you couple to a low dimension operator on the right. This is like your microscopic degrees of freedom that you're coupling. So in that sense, even though it looks similar, it's actually kind of a different type of coupling. And I think it's interesting to understand better the relation between those things. Oh, I'm sorry. Thank you. And then the
Ben?
yes.
A question? Comment, actually. I don't think it was important that these psi i's are what you call microscopic degrees of freedom. I think any low energy field would suffice, so long as you have enough of them.
Yeah, so that's maybe the question is how many you need, actually. So that's maybe another way of saying it. Like, do you need, you know, like n fields to be coupled or not? Okay? So, yeah, so that brings me to the other thing that I relate this to. So what do we have here? I'll erase it at this point. So we had, hopefully you know by now, so we had this chemical potential. And then we had this coupling. Now, the previous thing I did on traversable wormholes, or bubble, is in a paper with Cottrell, Hoffman, and Loconda. So there we had a very similar looking thing. We didn't have this chemical potential. Actually, Daniel told us to put this chemical in. That was a very good idea. We should have done it a bit faster. We would have been before this Millikan paper. But it was a great. A small number of operators. All right, again, you know, integrated in space, but a small number of low dimension operators. And it's interesting to try to, so the situation, the status of these two things is actually rather different. So here, we know the bulk solution. In the interesting range of parameters, we have a traversable wormhole. And we don't know the CFT state. Other than saying it's the ground state of this thing. But we don't know it explicitly. In this construction, and also in this case, then the gap is small. I think it must be. So there must be some, so maybe I should have listed this as 5, what is the CFT state? Yeah, so of course the bulk geometry, it looks a lot, you know, it looks close to the Reisner-Nordstrom black hole for a long time. So it seems like it must be like a version of the TFT state with chemical potential. But on the other hand, since it's like super extremal, it's like you're probably in a weird regime of that. And then obviously you have some correction due to this thing. So I don't know if it's close in the sense that the fidelity is close to 1, or if it's close in some more coarse-grained sense. In this case, we claimed that the ground state is very close to the TFT state. Although I look forward to talking to people here who I think maybe might question this result. But in this case, so the reason that Daniel told us to add a chemical potential is that in this case we have no semi-classical bulk dual. Right? We want this way to prepare the TFT state, And then we were going to evolve by getting rid of these things. But if we consider, like in this talk, just evolving with this Hamiltonian, we think we know what the ground state is, but we don't have a bulk description. And in this case, the gap is claimed to be of order the temperature. Or let's say order 1 in this. So that there should be some whole way of interpolating between these two things and even connecting to this Model-Energy construction. You know, you might like to get to some regime where you can understand the bulk. You can also understand the T dual. Okay? So, anyway, I think there's kind of many fun things you could try to do with this kind of construction. And it's also quite a tractable thing. So, yeah, I hope to hear from you what the most interesting questions are. Thanks.
We have time for a few questions.
Sorry, maybe a very basic question, but when you wrote the vacuum, the expectation value of the Hamiltonian, I'm sorry, it's already right.
Yeah.
But, you had these factors of Gn, of G Newton, and you said that you needed mu to win over the first two,
Yeah.
two terms. These are, I think you commented something a little bit, because the first two are 1 over Gn, and the other one is 1 over square root of Gn.
Yeah.
So you actually would need mu to scale a square root of Gn to win over them, or not, but I am understanding this getting.
Yeah, so at least in some conventions, the chemical potential should be Planck scale. That might sound concerning, but I don't, it just means kind of like if you have a Planck mass particle with charge 1, then that chemical potential encourages you to produce that thing. I don't think that causes you to lose some kind of control. Like, I don't think there's any like bulk quantity that's large. I did have a vague feeling of concern, but it's true that this critical value of the chemical potential is, you know, is Planck scale.
No further questions. Let's thank Ben again.